Hello, everyone. Uh, Today it's our great honor to invite Professor Luke Bisby from University of Edinburgh to give a webinar talk about the playing with the fire unplanned adventures in fire science, engineering, and psychology. Now you can see I'm sitting in my class, the fire dynamic English class, and with the 75 first year graduate students. Okay. And Professor Luke Bisby is a professor of fire and structure of the School and Engineering at the University of Edinburgh. After a bachelor in civil engineering and applied mechanics at McGill University in 1997 and a master's degree in structural engineering at Queen's University in 1999, he obtained his PhD in structural engineering at Queen's University in 2003. And Luke Bisby is very active in both academia and industrial. He is currently the editor-in-chief of Fire Safety Journal and currently the head of the Research Institute for Infrastructure and Environment at Edinburgh. Okay, so let's welcome Professor Luke Bisby's talk.
Okay, so thank you, Yuang, and hello everybody. And it's wonderful to see such a large crowd of people to hear my talk. One of the things that Yuang didn't mention in my introduction is that I'm also a visiting professor currently at USTC, which is of course a huge honor for me. So I'm doubly pleased to be giving this talk, both because I think the SFPE student chapter is a very important part of the fire safety community, and because of my role as visiting professor at USTC. And I want to thank Yuang for organizing that role and for inviting me to give this talk. So the talk that I'm giving today is not a technical talk. It's a talk about when I speak with students, often a question that I get is sort of, how did you become you? How did that happen? And that sounds sort of very egocentric, but the point of it, I guess, is to try to get people to relax a little bit and to just follow the things that they think are interesting, and to suggest that if you do that and you work hard, that you can be quite successful and that you'll have an interesting and fulfilling academic life. So that's the point of the talk. So it's really just my story of how I became, a chair in engineering, working in fire safety, and apparently someone who's had some success in his professional life. So an alternative title for this talk could be, how on earth did this happen? How did I end up in this position as being someone who apparently is considered an expert within the fire safety community? So that's the point of the talk. And I hope, despite starting late, I hope we'll have some time for some questions at the end if people want to ask me some questions. So I said that this talk would be an egocentric talk, and egocentric is a word, I don't know if it translates well to Chinese or to people who have English as a second language, but there's sort of two meanings for the word egocentric. One is that it's a very selfish or self-interested way of looking at things, which is not what I'm trying to do here. And the other is that it is, which is the bottom definition showed on this slide, is that it is centered in or arising from a person's own individual existence or perspective. So I want to give you my perspective on how it is that I've ended up, a senior academic working in fire safety. And when I'm asked to give advice, I always say that the key thing I think to remember about an academic or about life in general is that my approach to kind of finding myself where I am has been to make sure that I'm interested. So I'm interested in what I'm doing, which means that I'm probably enjoying myself if I'm interested. But that's not enough. It's not enough that you're doing something that you find interesting and that you're enjoying doing. That thing that you're doing also has to be interesting to other people, so that people will want to join you, will collaborate with you, will want to give you funding, will want to pay you a salary, and will want to permit you to do that and earn a living doing it. So you have to be interested. You also have to be interesting to other people. And I also take the view that you should try in general to be good. You should try to do good in the world, whatever that means, which is why it's in quotation marks. And the easiest way to do all of those things is to make sure that you've surrounded yourself with exceptional people. So I mean, a good example of that would be Yu Wang coming to the University of Edinburgh to work with my colleague David Rush and myself. And if you surround yourself with people like people like Yu Wang, then it's very easy to be successful. So with those points in mind, I want to tell you sort of the story of how it is that I got here, because many people assume that someone who is in my position had a plan when they were a university student, that this is where they wanted to somehow end up. And I've never had a plan. And I want to show you how it happened. So I guess, firstly, I would say I think I became an engineer, or at least the first hints of becoming an engineer happened when I was very young. And I loved, for instance, Lego was by far my favorite toy. And we had a huge tub of Lego in the basement of my house, where my brother and I would play with Lego constantly and build things. And so I was very interested in building things, and you can learn a lot of really interesting physics from Lego. And so I did that. And when I was 9 years old, I moved to a city in England called Bristol, and I lived there for slightly more than a year. And I lived very close to this bridge, and this is a beautiful suspension bridge, quite an old suspension bridge, which was designed by an English engineer called Brunel. And Brunel was a real early genius of engineering and bridge building. And I thought that this structure, which is called the Clifton Suspension Bridge, was absolutely exquisite. And I immediately fell in love with the idea of building bridges. So, again, it was all about building. And then when I was a teenager, I got very interested in skateboarding. So I was, this was the 1980s and the early 1990s. And I got very interested in skateboarding, and I spent a lot of time building skateboard ramps. It became a bit of an obsession. And again, you can learn a lot of interesting physics from building skateboard ramps, because you have to understand things about curvature and trajectory and velocity and projectile motion if you want to build the perfect skateboard ramp. So that got me really interested in physics. So you combine a love of building with a love of structures and a love of physics, and you end up, at least in my mind, wanting to study architecture. And I decided that if I could mix my love of building with my love of structures, with my love of physics and a love of art, that I would end up being an architect, and I would design beautiful structures. And this is an example of one of my favorite structures. It's a house called Falling Water, which was designed by Frank Lloyd Wright, and it's in the United States. But it turns out that I can't draw very well. I can't draw artistically very well. So architecture didn't actually become an option for me. What did become an option for me was that I found that I was very, very good at technical drawing. I was very good at drawing, for instance, gear sets and differentials and pieces of car, very, very good at technical drawing. And so that led me to go to McGill University in Canada to study engineering, and I earned an undergraduate degree in civil engineering. And at that time, I was really focused on structural engineering. I had intended to design bridges and high-rise buildings, was what I was interested in at the time. And then I graduated from McGill University, and incidentally, I like to look at the mottos of universities. I don't know what the motto or the slogan of USTC is. Maybe someone can check that and can tell me after the talk. But at McGill University, the motto, which is shown here on the crest of McGill University, is "Things grown great, increased by work," which I think is a great motto for the theme of this talk. So things will become great if you work really hard, which is one of the things that I would always like to say to students. But anyway, when I graduated from McGill, and I was going to get a job, and I thought I would be a bridge designer or design high-rise buildings. Unfortunately, fortunately or unfortunately, I then met a girl. And this girl, who I was very interested in at the time, lived in a small town. And this small town was called Kingston, Ontario, which is a town of 100,000 people, which in the context of Chinese cities is probably not even a village. It was a tiny little place. And in this town where this girl lived, I wanted to go and live in this town where this girl lived. And there were no engineering jobs at all in this town. But there was a very good university, and that university was called Queen's University. And so I couldn't get a job, but I could continue going to university if I wanted to be close to this girl that I was interested in. And so I decided that I would move to Kingston, and I would try to continue going to university, which meant that I would do a master's degree. And so I went and I signed up to do a master's degree. And of course, I had to decide what area of engineering I was interested in doing a master's degree in. And around that time, I happened to be reading an engineering magazine, and I saw a proposal, which was a proposal that had been made by an engineer called Urs Meier, who was a very skilled Swiss engineer who worked at an organization called EMPA just outside of Zurich. And he had proposed a cable-stayed bridge that would link Spain to Africa across the Straits of Gibraltar. And this is a sort of a grainy picture of what he had proposed. And you can see on this drawing that the central span of the bridge that he had proposed was 8,400 meters. So that's 8.4 kilometers. Now, China has a lot of long span bridges in it, but it doesn't have any bridges that are that long. In fact, the longest bridge in the world right now is a suspension bridge in Japan, I believe, which has a central span of 2 kilometers. So less than 1/4 of the central span of this bridge. Not only that, this bridge was to be a cable-stayed bridge, not a suspension bridge. And the important thing to recognize about this proposal is both that it's exceptional in its scale. It completely changes the game of what would be possible in structural engineering. But the really key thing to understand about this proposal is that a bridge of this length is only possible if the cables that are holding up the bridge deck are made from carbon fiber reinforced polymers. Now, carbon fiber reinforced polymers are very, very strong, very, very stiff materials. So they have an extremely high strength to weight ratio, about 5 times that of steel. And if you tried to make a bridge like this using regular steel bridge cables, the cables would be so long, some of these cables would be 6 or 7 kilometers long, and they would snap under their own weight. They wouldn't be able to be that long without snapping under their own mass. So only using carbon fiber could you build these structures. So I became really, really interested in the idea of using carbon fiber reinforced polymers, CFRP it's called, to design structures. And I thought, I'm going to do a master's degree in that area. So I want to study that. So I did. Now, before going on, just to point out the scale of this bridge, I'll just go up to point out the scale of this bridge. You can see that the taller of the two towers is 1,250 meters tall, which is sort of about twice the height of the tallest building in the world right now. And the shorter tower is 850 meters tall. And just to put it into scale for you, because I suspect that you're all in Hefei right now, that's the tallest building in the city where you are, as I understand it. And it is, I believe, 218 meters tall, which is quite a tall building. And if I just put that to scale on this slide, that's how big it is. So this bridge is absolutely immense as a structure. So anyway, so I went to Queen's University. This is the crest of Queen's University in Canada. And I did a master's degree looking at carbon fiber reinforced polymers. I also like the motto of this university, which is that wisdom and knowledge shall be the stability of thy times. Certainly living in the United Kingdom, I don't think that's actually true at the moment. But I went to Queen's University and got my master's degree. And then during my master's degree, I actually got very interested in two things. I got very interested in research. I realized that I really did love research. I loved understanding more about the world. And I also learned that I love teaching. So I really enjoyed speaking to people about the things that I knew and helping them to also understand the world. And during my master's degree, I also got interested in this particular application of carbon fiber reinforced polymers, which is wrapping concrete columns to make them strong. So if you have a concrete column in a building and you wrap it in the hoop direction, in the circumferential direction, with carbon fiber reinforced polymer that can really immensely strengthen the column and really increase the ability of that column to deform under loading. So it's very good for strengthening of existing structures, and it's extremely useful for earthquake retrofit of structures, so to make structures more able to resist earthquakes or seismic events. And this is just an example. Hopefully this video will play, but this is just a concrete column that's been wrapped with carbon fiber. And I'm compressing this column down, so I'm pushing down on the top, and just to show you what happens. So I spent a lot of time studying the strengthening of concrete columns with carbon fiber reinforced polymers and how they fail and how we can predict the load carrying capacity of these really interesting structural elements. So that's the failure of one of these columns at 5,000 frames per second. So the failure is very explosive and very violent. And I spent a lot of time trying to understand that. Now, one of the problems with columns that are wrapped with carbon fiber in this way is that in order to get the carbon fiber attached to the concrete column, you have to use epoxy. And epoxy is a polymer, and it's combustible, and it actually will burn quite enthusiastically if you give it the opportunity. And so in my PhD, that became the topic that I was studying. I was trying to understand the fire resistance or the way that these carbon fiber reinforced polymer strengthened columns would react in a fire. So we built some big columns out of reinforced concrete, and we wrapped them with carbon fiber, and we insulated them with fire protection insulation, and then we subjected them to full-scale fire tests at the National Research Council of Canada. And I spent then a lot of time learning about fire resistance testing, learning about the way materials and structural elements respond to heating, learning about the structural response of buildings in fires. And it's important for me to say that I started my PhD in this area in 1999. So in 2001, I was about halfway through my PhD, and I woke up one morning and I went into the office and I sat down at my computer, and I got a phone call from my girlfriend, and she told me that I had to turn on the CNN website because a plane had crashed into the World Trade Center. And so I did, and I sat there and I watched this event unfold in front of me. And you can imagine I was one of a small group of people in the world at that time who was actually spending their entire life, and had been for 2 years, studying the way that building columns react to fire. And so this event all of a sudden made the thing that I was studying a very important topic. And for about the next 10 years, the work that I had been doing on concrete columns and in fire had a lot more attention, I think largely because of 9/11. So one of the things that pushed me in the direction that I now am was actually this horrible disaster that unfolded in the United States. It's something completely out of my control and is entirely serendipitous, entirely accidental that this happened. And shortly after that, shortly after 2001, somewhere around 2002, I met this man. Now, I don't know if any of you know who this is, but this is a fellow called Jose Torrero. This is Jose Torrero quite some years ago. He's a bit older now, as am I. And Jose is a very charismatic guy who worked at that time at the University of Edinburgh. And he and I had a mutual friend, a guy called Jason Gerhard, who now works at the University of Western Ontario in Canada. And Jason had come to Edinburgh after his PhD and was working here as an environmental engineering professor. And he introduced me to Jose Torrero, and Jose and I got on very well. And Jose asked me to come and work at the University of Edinburgh, effectively. And so I started looking at the work that was being done at the University of Edinburgh at that time. And I started looking, for instance, at the work of Professor Asif Usmani, who now is a professor in Hong Kong at HK Poly U. And at that time, Asif and his colleagues and Jose were doing things like this. This is a finite element model of 6 floors of the World Trade Center towers, 1/4 of 6-floor section. And they were doing modeling to try to understand how the structure reacted to fire. And this is just a simulation of one of their collapse scenarios for the World Trade Center towers with a fire over 3 floors. And you can see what they predict happening is that you get a kink in the column as the floors deform in the fire and they pull the column in. And I thought this work was absolutely fascinating. Here's just a section through the same simulation. So on the right-hand side is the core of the building, and these are the office areas in the middle, and then this is the perimeter column on the left-hand side. And if I just let that play, you can see the collapse scenario. The floors sag as a consequence of the heating. The outside column gets pulled in by the floor. You get a hinge forming in the column, and you initiate a collapse scenario. So what they were doing was they were doing these really sophisticated finite element models that were predicting the structural response of a building in a fire by considering more holistically the behavior of the entire structural system. And they were discovering really interesting things about the way these buildings performed and about the factors that are actually most important when we think about the structural response of buildings in fire. And this really spoke to me, this idea that we should be thinking about the way structural systems respond to heating rather than looking at the way individual elements respond to heating. Because I had done my PhD looking at the response of individual columns tested in a fire resistance furnace, I had this idea that that was not an appropriate way to be doing things, that furnace testing of individual elements wasn't actually capturing the physics that needed to be captured if we wanted to predict the way that a building would respond in a fire. And so having met Jose Terrero and having seen the work that was being done by people like Asif Usmani, as well as, and that work was being done in collaboration with students who would go on to work at Arup, the large engineering company. I then, around that time, also met the man that's shown in the top right corner on this slide. And his name is Sir Duncan Michael, and he was the former chairman of Arup. And then I spent the following 10 years working as an Arup-funded reader, which is like an associate professor, and then as an Arup-funded chair for almost 5 years, looking at the response of structural materials and structural elements and building systems in fire. And that's kind of what pulled me more and more into fire. And of course, by association with Arup throughout that 10-year period, I got involved in lots of interesting discussions about other factors that we should be thinking about in the engineering, in the fire engineering of structures. So that is how I came to the University of Edinburgh. And that was in around 2008, after I'd been an assistant professor at Queen's University in Canada for about 5 years. The motto of the University of Edinburgh, incidentally, which I think is also a very interesting and good model, is neither rashly nor timidly. So what they're saying is you shouldn't be so timid in the world that you can't get anything done, but you also shouldn't be so rash or so aggressive that it pushes people away from you. So you should try to find a middle ground between being timid and being rash, which I think is a really nice way of thinking about how to be in the world as well. And one of the things that's interesting about the University of Edinburgh, that with hindsight, I think is, just as an aside, quite interesting, is if you look at the logo or the crest of Queen's University, where I had been educated in fire engineering, and you look at the crest of Edinburgh University, you see that they're actually very, very similar. And I subsequently discovered, I didn't know at the time, I discovered that Queen's University had actually been modeled on the University of Edinburgh when it was created in the 1800s. These funny connections that we see later in life that we don't realize at the time. So anyway, so I came to the University of Edinburgh as an Arup-sponsored reader, and I spent a lot of time looking at what had happened in the 9/11 events. And one of the things that happened in the 9/11 events that many people, my slides are not happy here. One of the things that happened in the 9/11 events that many people aren't aware of is that there was a third building that collapsed at 9/11. The building was called World Trade Center 7. It hadn't been hit by an airplane. It simply collapsed and fell down. And the collapse of that building looks a lot like a controlled demolition. And there was a lot of work done to try to study that collapse, because obviously it hadn't been hit by an airplane, and there wasn't impact damage from the aircraft, and there hadn't been any aircraft fuel exposure. So there was no view that the fire had been more severe. And so World Trade Center 7, it turns out, was a building that just simply collapsed because it was on fire. So you had a total collapse of a building because it was on fire. And this is something that hadn't really been observed before, the total catastrophic collapse of a building on fire. And so a lot of work went into trying to understand how that might happen. And I got to thinking over many years about those collapses, that a building on fire could completely fall down catastrophically. And that the engineering community didn't appear, strangely from my perspective, that interested in understanding how that had been. And then I also spent a lot of time reading about engineering failures. And one of the things that I'm interested in about engineering failures is why failures happen fundamentally, and what the engineering community does then to learn about the failure and to unpick the root causes of the failure. And so if you take Tacoma Narrows Bridge as an example, the Tacoma Narrows Bridge, many of you will have seen these videos before. The Tacoma Narrows Bridge was a very innovative, long-span bridge, very slender, that experienced a really unusual wind-induced oscillation that eventually led the bridge to collapse. Now, nobody was killed in this collapse. There was a dog in the car that you can see on the bridge there that was killed, but no humans were killed in this collapse. And yet the engineering community spent a lot of time and a lot of effort trying to understand the causes of this collapse. And how it could understand the physics that had led to this strange wind-induced oscillation, how it could understand how to prevent such things from happening in the future. And one of the consequences of the Tacoma Narrows Bridge collapse was that wind tunnel testing, for instance, was in its infancy at the time. And subsequent to this collapse, wind tunnel testing of long-span bridges became just something that you would do. So you would, if you were designing a long-span bridge, you would spend a lot of time and a lot of money to undertake wind tunnel tests of your bridge to make sure that you understood that nothing strange or unusual was going to happen to it. And if you contrast that approach with the way that we still design structures to resist the effects of fire, which is still predominantly done on the basis of, the fire resistance of that beam is 60 minutes, the building will be fine, without thinking about the system effects and without deeply understanding the physics that's underlying that. If you contrast how engineers currently, structural engineers in particular, currently deal with the effects of wind when designing high-rise buildings, for instance, with a great deal of sophisticated computational modeling of the whole structure, computational fluid dynamics modeling of the wind environment around a building, scaled and very expensive wind tunnel testing to experimentally study the behavior of the building to resisting the effects of wind. And you compare that to design for fire of most high-rise buildings. These two issues are worlds apart. But why did Tacoma Narrows, an event that didn't kill anyone, cause such a rethink in the structural engineering community, whereas the collapse of World Trade Center 7, which also didn't kill anyone directly, caused the structural engineering community to really not do anything of any significance? And I think that's a really important question. And one of the things that's driven my work in terms of looking at the standard fire resistance test, trying to understand what it is and what it's not good for, and trying to get people to think a bit more holistically and to treat fire as a design load in the same way that we would treat wind or gravity or earthquake when we design these high-rise buildings. And that's really been the focus of much of my work for the last 10 years or so. So then I came to Edinburgh, and I've been at Edinburgh now for 14 years. And in my time at Edinburgh, I've gotten involved in a lot of really interesting projects across a huge range of areas relevant to fire safety. So this is a picture of a building, a rendering of a building, the tallest building in Central Asia, which experienced a very significant construction fire. I've done a lot of work looking at the use of timber in high-rise construction and a whole host of fire safety considerations associated with that. And there are many to think about that are not yet thought through properly. Done a lot of work looking, for instance, at fire protection coatings that are used in the oil and gas industry. So intumescent paints that are used in the oil and gas industry. Work looking at concrete tunnel linings and fire-induced explosive spalling of concrete over many years with colleagues. have gotten involved in work looking at fire safety in informal settlements. Yu Wang came to Edinburgh to work in this area, so that's how I got to know Yu Wang. Just to throw in something else that I do, I think it's important to have other interests outside of your core interests. So I've been doing work for many years now looking at, again, carbon fiber reinforced polymers that are used as tension elements, for instance, in America's Cup yachts, and interesting applications of carbon fiber reinforced polymers in structural use, where their very high strength to weight ratio can be used to great advantage. So just to show you very quickly some examples of some of the work that I've been involved in over the years, this is work. This is a video of some work we did in conjunction with an organization called Sarib in France. And this was work we did large-scale compartment tests on full-scale compartments that had exposed timber in the inside of the compartment. So we were looking at the fire performance of essentially buildings that are built out of a product called cross-laminated timber, which is like really big, massive timber plywood. So really interesting large-scale experiments. I'm happy to talk about that. We've done quite a lot of work looking at the fire performance. Sorry, that's paused. Quite a lot of work looking at the fire performance of different types of facades. This video is not running very well, so I'll just show you some screen captures of it. So we've done a lot of large-scale work. This is a 9-meter tall test rig where we were interested in studying the effects of fire on different types of facades, and you can see some very large and very interesting fire experiments done there. This is a video showing some of the informal settlements work that I didn't participate in these tests personally, but I believe that Yu Wang was there. And these are tests on informal settlements in South Africa, where we're trying to understand the fire growth and the spread of fire within these informal settlements, where huge numbers of people live in informal settlements in the world, and fire safety in these situations is a very significant problem. So large-scale testing of those types of scenarios. And then also I've been involved, one of the things that I've realized through my technical work is that there's no point in doing very good technical work and understanding a lot about the world if you can't convince people that that work matters in practice. And so I became very interested about 10 years ago, thanks mostly to Sir Duncan Michael from the Ove Arup Foundation, in issues around education, sociology, and regulation in fire safety. And I met these two gentlemen, Graham Spinardi and Robin Williams, who I've learned an immense amount from. And that led me to do work, for instance, on education for fire safety engineering. So what educational framework should we use to try to educate people who work in fire safety engineering? I got interested in the sociology of fire safety. So how do fire safety scientists and engineers think about their knowledge and use their knowledge in application? And did some work with Graham Spinardi, shown there. And I've also done some work looking at the regulation of fire safety in the construction industry in the United Kingdom, and have published in that area as well with Graham Spinardi. And this has led me to think much more deeply about the technical knowledge that I have, and to think much more widely about how to make that technical knowledge relevant in the practical, real world. And I think it's really important for fire safety engineers to be aware of the social context of their work. And of course, I work long hours and I work very hard, but you do need to have a hobby, I think. And so my hobby has been to get involved in this television program over the years called Impossible Engineering. And being involved with Impossible Engineering has given me an opportunity to do something that isn't my work, but that is interesting to me and sort of related to my work, and to go around the world and visit really fascinating engineering sites, and to learn the history of those engineering sites, and to climb on them and in them and fly over them, and do lots of various interesting things that most people would not have an opportunity to do. So that's been something else that I've gotten involved with. I got involved with Impossible Engineering as a consequence of giving a talk about fire safety engineering, and a journalist who was at that event was interested in what I had to say and put me in touch with a production company, and they just contacted me. And because I'm interested and because I try to be interesting, I thought this would be a fun thing to do. And it's turned into now, I think, 6 seasons of Impossible Engineering that I've been involved with. One of the real beautiful things about my work in Impossible Engineering was that one of the episodes of Impossible Engineering that we filmed was interested in a bridge in Greece. And one of the backstories that we used in that episode to tell the story of bridge engineering was this Centennial Bridge in Switzerland, which is this really exquisite concrete arch structure in Switzerland. And in order to talk about that bridge, we wanted to find someone in Switzerland who was a bridge engineer who would be able to talk authoritatively about this structure. The person that the television production company ended up using was Professor Urs Meier. And if you remember what I said earlier in my talk, Professor Urs Meier is the person who, in the late 1990s, when I was trying to decide what I wanted to do with my life, it was a proposal by Professor Urs Meier to build this bridge over the Straits of Gibraltar that led me into a master's degree in engineering, and eventually led me to be involved with Impossible Engineering over the course of my career. And he was the person that we ended up working with on the Centennial Bridge. So there's a really beautiful, I think, circularity to that kind of relationship. So he's the person that had proposed that bridge that I put up earlier, and it's wonderful to meet him. And I now do work with Urs Meier's former students. So people who I work with currently are students who worked with Professor Urs Meier at the same time that I was inspired. I guess in summary, my entire professional career has never been planned. I am a beneficiary of circumstance, if you like. But I think that the things that I have done within the circumstances that I've lived in can be summed up as trying to be interested, trying to be interesting, trying to do good wherever I can, and surrounding myself with exceptional people. And on that last point, surrounding myself with exceptional people, as a visiting professor at USTC, I hope that I will have the chance to meet some of you over the course of the next year, either virtually or perhaps, if the world permits it, and travel rules permit it, perhaps in person, and hope to have some more unplanned adventures with some of you. Thanks very much for attending today.
Okay, thank you, Luke. Thank you for a very nice talk. And then we will have a Q&A question. So if the other audience, if you have any questions, you can leave a message in the chat box. And I will also ask the students in the classroom. So anyone has questions? Hello, Professor Bisby. Can you help me?
Yes.
Okay. I have a question. How do you get out when you encounter difficulties in life, such as emotional confusion, learning trouble, and occupation stress? Yeah.
It's a good question. Yes, I have quite a lot of occupational stress. It's a very good question. I mean, to be perfectly honest, I every Wednesday right now, every Wednesday at 12 o'clock, or sorry, every Wednesday at 11:30 in the morning, I walk out of my office and I walk into the center of Edinburgh, which is a beautiful city, by the way. And I go and I sit down in a quiet room with a psychotherapist for 1 hour. And I speak with the psychotherapist about my life for an entire hour. So for more than 10 years now, I've been doing that. And I think it's really important. I believe that physical health and mental health are equally important. And I believe that if you want to be physically healthy, what do? You exercise, right? If you want to be physically healthy, you go for a run, or you go to the gym, you lift some weights, you run marathons, you do things actively to be physically healthy. And I think if you want to be mentally healthy, you have to do the same thing. And I think the way you exercise mentally is by speaking to someone about your feelings. So that's what I do.
Okay, thank you. Okay, thank you for so any other questions? Okay. Oh, same a couple questions.
Where do you see the most successful in industry or academia? Because as Professor you introduced, you were doing both, and as how we have seen the biography was showing same. I hope my questions are clear.
Yeah, good questions. So the first one was, where do I see, I guess more success? Or the first question was sort of about academia versus industry.
And
right?
industry, yeah, company.
Yeah.
Where do you see yourself?
I don't think. I mean, I don't necessarily work in industry. I work sometimes with industry. And I think there's an important distinction. So I don't, I've never worked for a company. I've worked with companies as an academic. So I mean, I think I am absolutely an academic. The joke is that I've never had a real job. I've only ever been an academic. But I think you can be very successful as someone who works in industry if that's the path that you choose. I don't think academia is better or worse than industry. I think it's different. So I think it depends what kind of life you want to have. Academia is a wonderful job. For me, it's the best job in the world because in academia, the goal is to do interesting things that you want to do that matter in the world. And so long as that's true, and to inspire young people if you can. And so long as you're doing those things, then you're a successful academic. That's great. You don't have a boss. You don't have deliverables. You don't have timesheets. You don't have clients. You don't have shareholders to deal with. You just do things that are interesting, and you do them because you find them interesting. And I can't think of a better job or any other job that allows you to do that, to be honest. So that's one of the reasons I love being an academic.
Hi, Professor. Hi, Professor Luke Bisby. My name is Hongli Yiruan. I'm a student of Professor Yu Wang. My undergraduate study is GIS, not FI. My personal feeling is that this direction is not related to FI. Would you please tell me whether this professional transformation is appropriate? Thank you.
So what is your undergraduate degree in?
GIS.
GIS.
对 geography. Yes. 对。
I think that's absolutely appropriate. We over many years, I mean, Professor Yu Wang will know very well, and is very close, I think, with Leslie Gibson. And Leslie Gibson was a researcher at the University of Edinburgh who I'm sure if you're working with Yu Wang and you're working with GIS, you have heard the name Leslie Gibson. And I think GIS is extremely important for fire safety. And the two ways in which I think it's really important, one is when we look at issues around informal settlements. I think that GIS provides many of the tools that allow us to understand the structure and the materiality of informal settlements, which is hugely important for fire risks in those environments, and also in wildfires. GIS is obviously very important when we try to understand wildfire hazard or forest fire hazard. So I think, and it's important to say that very few people, I think, who work in fire safety have a first degree in fire safety. because there aren't many first degrees in fire safety in the world. Most people who work internationally in fire safety have first degrees in something else. I don't have any degrees in fire safety. My degrees are all in civil and structural engineering. And I think of my colleagues here at the University of Edinburgh, none of them have first degrees in fire safety engineering. So, a professional transformation from one area into fire safety is absolutely appropriate. Yes.
Thank you.
You just have quite a lot of learning to do.
Yes, yeah.
Hi, Professor Bisby. Thank you for your speech. And I have a question that how do we find ourselves suitable for scientific related work? I think the interest sometimes may not be enough to motivate us to do this job as a life career. Thank you.
Sorry, can you ask the beginning of that question again?
How do we find ourselves suitable for scientific related work?
Ooh, I mean, I don't know that I can answer that question for you. I have always said when students, because I'm quite a senior academic and because I hope that people find me quite approachable, I often have students ask me questions like that. What should I do with my life? What's your advice? What should I do? And I don't like that question because it makes me uncomfortable because it's not my life, it's your life. And I think that everybody should always make those decisions thinking about what can I do that I am going to find interesting? What can I do that other people are going to be interested in so that other people will pay me for it because I need to earn money because I have to, buy food and stuff. And how can I try to do good in the world? And so if you think you can do that with fire safety, that you're interested in fire safety and that you can do good and people will find what you're doing interesting, then you should do it. But if you're not interested in fire safety, that's fine. And you should try to find that thing that you're interested in. When I speak with young children, which I do sometimes, children who are maybe 12 or 13 years old and they're in school and they're trying to decide, what they might want to do at university. What I usually tell them to think about is when you're not at school, when you have a day off or it's the weekend or something, what do you want to do? What do you want to do when you're not at school? And maybe someone says, oh, I don't know, it doesn't really matter what they say. And then I say to them, can you think of a way that you could do that and get paid for it? Can you think of a way that whatever it is you want to do on the weekend when you're not at school, could you do that and get paid for it? Is there any way to make the thing that you would do anyway your job? And if there is a way to make the thing that you would do anyway your job, then that's got to be the right thing to do. So for me, like I love playing with Lego. I love the idea of bridges. I love building skateboard ramps. And I thought to myself, how can I get paid to do basically that? To think about the physics of how we build things. And that's how I ended up getting an engineering degree. And it's worked out beautifully because, one of the questions that I see in the chat is how do you balance your work and how do you balance your work and your family life? So work-life balance is the question. And the answer is sort of like, I don't, because I don't consider my work to be work. I consider my work to be life. So I have life balance. I don't have work-life balance because my work doesn't feel like work. My work is fun. I enjoy what I do. And if you enjoy what you do, then you never work. You're always having fun. So I think that is a very long-winded answer to your question. But I think that the answer is only you can decide what it is that you enjoy doing, and that you should try to find a way to do that and get paid for it, if that helps.
Okay, thank you very much.
You're welcome.
Yeah, so thanks to Luke's answer. I find there are some questions in the chat box. So I think you already answered the first question, right?
Yeah.
The balance, yeah, between work and it's kind of balance between life and life. So the second question is from Ding Pengfei. It's about thank you for your impressive presentation, Professor Bisby. My question is that how to better integrate fire research with the needs of firefighting and rescue?
I don't know if if that question is specific, or if that's a general question. In general, I think the way that we do that is by talking to the fire services more, whether as researchers or as designers. So, you know, I think it's important that academics talk to the fire services and understand their concerns and understand the things that they think are important. But I think most importantly, it's just important that when people are designing things, that they genuinely consult with the fire and rescue services. But it's also very important that the fire and rescue services upskill and increase their competence to understand the physics of fire. Most fire and rescue services, the recruitment and the training of the individuals who work within fire and rescue services is not at all focused on fire safety science. And that's a problem, because I think it's very important to understand the physics of the thing you're trying to do. So I think that we just need to have a closer communication. Academics and designers need to understand a lot more about the way the fire service operate, and the fire service needs to understand a lot more about physics. So, and we accomplish both of those goals just by talking to each other more.
Okay, thank you. Thank you for the. So any other questions from students here? So, okay, one more question.
Hello, Luke. Hello, Professor Luke Bisby. My name is Xiating, and we know that you are involved in many fields. And how do you find a new idea in a field? And could you please give us some advice? We are just beginning to do the research, and do you have some advice to us? Thank you.
I mean, when I was young, I spent a lot of time reading, reading research papers. Many research papers at the end will have like a recommendations for future research. So I would just read, what are people doing? What do they think is the next step? And then I would try to move quickly and do something that was relevant to that question. Now, to be honest, the research questions that I end up being interested in, that I end up doing work in, kind of present themselves to me. I don't go looking for them. They just kind of arrive on my doorstep, if that makes sense. So for instance, right now I'm doing a lot of work to understand high-rise timber buildings and fire. But that just kind of happened spontaneously because I went to some meetings in Europe, where people, I got invited to go to some meetings in Europe about a network of academics in Europe who were studying fire safety of timber buildings. And because I'm interested in things, I thought I would take the time to go to the meeting. And then when I was at the meeting, I realized this is really interesting and there's a lot of unanswered questions and interesting physics. And so I just did it. And then with all the work that I'm doing in cladding at the moment, this horrific fire happened in London, and I was asked to look at the physics. So we started looking at the physics, and then I got very interested in the physics. I had been interested previously, but I got really deeply interested in understanding the physics. And now, that just leads to a lot of interesting questions that I want to answer through research. So the way to find interesting research projects is to be interested. And if you're interested, you will find them. In being genuinely interested in something is not something that you can turn off or even control. If you're genuinely interested in something, it just happens, right? That's how you know you're doing the right thing, because stuff just happens. I don't know if that's not a very helpful answer, but as a student, I would say, read everything. Read. Go to meetings, go to conferences, talk to people, read. Yeah.
Okay, thank you so much.
You're welcome.
Okay. Yes, this is what I often tell my students. Read more people again and again. Okay. So I believe there are no other questions. Okay. And I believe there are a lot of information from Professor Luke Bisby talk, and I think including me and the other students and some other audience also learn a lot from your talk. And we would like to thank you again for Professor Bisby's talk. And thank you very much, Luke, for your presentation. And
Thank you, Yuang. Thank you for the invitation. I really appreciate it. And thank you for coming, everybody.
Yeah, okay, thank you. And more activities will come in the future, because this is a kind of SFPE, Hefei Student Chapter webinars, serious webinars. So let's see you again in the future. Bye, everybody.
Of course.
Yeah.
Thank you. Bye-bye.
Thank you. Bye, Luke.